In this video, we're going to go over how to analyze titration curves, also known as titration graphs, and we're going to just pick out important information, and then we're going to calculate the concentration of our samples based off of the curves that we've been given. So in the first example here, we've been given 25 milliliters of acetic acid is titrated with a 0.04 mole per liter solution of barium hydroxide. Okay, so just reading this sentence here, there's a couple of bits of information that's already given to us. So we're told acetic acid is titrated with, so remember these are important words because whatever comes after that titrated with, that is going to be your titrant. So that's going to be what is in the burette. Okay, so that means that this 25 mils of acetic acid, that means that is going to be your sample. Okay, so if we look at our titration curve here, what we're starting off with over here, that is going to be the pH of our sample. So let me just get a smaller circle here. So what we're starting off with, this is our pH of our sample, which is acetic acid. So it makes sense that it's going to be around 5, a pH of 5, because acetic acid, obviously it's an acid, and if you want to look it up in your Chem data booklet, you'll find that it is one of our weak acids. So again, it makes sense that it's not going to have a super low pH just because it's not a strong acid, but it's still within a logical range for a weak acid. Okay. Another thing that we can tell from this pH curve, so barium hydroxide, well, that's a metal, so the metal being barium, that's hydroxide. Any metal with a hydroxide, that's going to be a very strong base, which if we look at our pH curve or titration curve, whatever you want to call it, you can notice that the curve ends at a pretty high pH, which makes sense if we're adding an incredibly basic substance here. All right. So we're going to use the information in the graph to answer a couple of questions. So we're asked to label the endpoint as well as the equivalence point on the graph. So starting off with the endpoint, remember the endpoint is the pH in which the color change occurs in the titration. So in order to find this, you're going to want to locate the steepest part of the pH curve or the titration curve, whatever you want to call it. So to do this, I like to just draw lines to help my eyes focus. Okay, and then in the middle of the steepest part, that's going to be where our endpoint is. Okay, so roughly about there, okay, is where our endpoint is going to be. So that's right about at an endpoint of 10. Okay, keep in mind, just with these graphs, there is a little bit of wiggle room for pH as well as your equivalence point volume. So with this, if you put it a little bit lower, like let's say 9.8, you said 9.8 was where your endpoint was, like that's going to be okay. So let's figure out what our equivalence point volume is. So just trying to draw as straight a line as possible here. All right. So looking at this, each of these tick marks is worth about 2 milliliters here. So I'm going to say that our equivalence point volume is about 33 milliliters. So again, just a reminder, there is a little bit of wiggle room with these. So if you got 34 milliliters, that's okay too. Okay. One last thing that I want to add to this question, just because it's on the next example there, is just labeling the buffering area on a pH curve. So let's just add that in. So the buffering area is just when the pH isn't changing a whole lot in the titration curve there. Okay, and it's just because buffers typically resist change or changes to pH. So right when you get that first plateau, or I guess it depends on how many acidic hydrogens your acid can give up if you are titrating a sample that is an acid. But typically where you're going to find those buffering areas is in either the first plateau or the first couple of plateaus. But the main idea is your buffering area is never, ever, ever going to be the last plateau. Okay, so here is where our buffering area would be. Okay. And once again, for pH curves, your last plateau is never going to be your buffering area. Okay, so this plateau right here, that's not going to be a buffering area. Okay, so next question is determine what indicator would be appropriate to determine the endpoint for this titration and what color change would occur for that indicator. So just to clarify this question, we're going to be writing about the color change that occurs from the start of the titration to the end point of the titration. Okay, so as we figured out before, the endpoint is at a pH of 10. Okay, so how we choose our indicators is we need to select an indicator which will have the endpoint roughly in the middle of its range. So you don't want the endpoint to be at the ends of the range, you want it to be right in the middle. So let's go to our list of indicators here. So for example, an indicator that would not work with an endpoint of 10 would be phenolphthalein because 10 is right at the end of its range. So you don't want to use that one. Okay, but if we look at thymolphthalein, which is right here, 10 is going to be in the middle of this range. Okay, so thymolphthalein is going to be a really good indicator to use for this titration. Now, if you're looking at alizarin, okay, so notice how like 10 is just below its range, right? And some people might think, well, it's close enough. Nope, the endpoint must be inside the range of the indicator. So just be careful about that. So we're going to say, okay, our indicator that we're choosing is thymolphthalein, and its color change is colorless to blue. Okay, so that's what we're going to be writing. So again, our color change that we're talking about, we're only going to be focused on where it's starting and what the color will be like at the end point. Okay, so at the start here, okay, we've got a low pH. So let's just go back to what I said. Okay, we're starting off at a pH at around 5. Okay, so if we look back at our data sheet, then we know that 5, or a pH of 5, is going to be below 9.4. So that means that this indicator is going to be colorless at a pH of 5. So it's going to start out colorless. Okay. And then at the endpoint, remember, since our endpoint is at a pH of 10, it's in between 9.4 and 10.6. So it's going to be the in-between color between colorless and blue, which would just mean light blue, okay, or a very faint blue color. All right, next part. Let's calculate the concentration of acetic acid. So in this question, we're only given the name of acetic acid, but we're not given the chemical formula of acetic acid here. But if we look at our data booklet, so if we go to page 9 here, you're going to find acetic acid right here, and you can find the formula for it right here. So CH3COOH. So with this, essentially what we're doing is now we're going to be getting into the 4 steps of Stoich that we need in order to solve for the concentration of acetic acid. Okay, so we were told that acetic acid is being titrated with barium hydroxide. So another way to say that is acetic acid is reacting with barium hydroxide. Okay, that'll help us create our balanced chemical equation. So barium hydroxide, and acids are always aqueous. With barium hydroxide, you might look it up in your solubility table, and it'll be solid or insoluble, in water. However, with titrations, they are done with solutions. So in this case, we are going to assume it is a solution. Why? Because the question tells us that, because a titration is occurring in this question. All right. Now, the trick with acetic acid, if we go back to our data booklet, is there's only a certain hydrogen that will be given up when it undergoes a neutralization reaction. Okay, and we can tell based off of the conjugate base formula, which is right here, that the acidic hydrogen is the very last hydrogen, because going from an acid to the conjugate base, we lose that last hydrogen. Okay, so just watch out for that, because it does matter which hydrogen you use. And what I'm going to do with that information is I'm going to use that to color code my ions. So hydrogen, in this case, that is our cation. So I'm going to be using blue to denote my cations or my positive ions. For barium hydroxide, barium's a metal. Metals have positive charges. So there we go. Okay, so we have a compound reacting with a compound here. And what we need to do is we need to have a double replacement reaction take place. So I usually like to just switch my positive ions or my cations. So hydrogen and barium, they are going to switch spots. So we're going to have our acetate ion. Now, acetate ions, they like to have a -1 charge. How you know that is because looking at the conjugate base formula of it, you can see right here that it has a -1 charge on it. Okay, now barium, because it's in group 2, so let's just see that for a second here. So barium's number 56, so it's part of group 2, and it likes to have a 2+ charge on it. So if I write barium here, we're going to need 2 acetate ions in order to balance out the barium ion. Another way that I've been saying this is we know that -1 plus 2 does not equal 0, so we got to do crisscross applesauce. Okay. Now, if you're wondering why I'm writing the cation afterwards, it's just to keep up with this notation where the acetate ion comes first. However, you could write it first if you want to keep up with cation comes first, anion comes after. Okay, both mean the same thing. Now I'm going to make sure that I have 2 of these. So because this is a polyatomic ion, I need to put brackets around it, especially when there are more than one of them. Okay, so that is balanced. I will worry about the state later. So in our first product, we took care of barium with the acetate ion, but now we need to take care of hydrogen going to live with hydroxide. So just HOH. Okay, if you want me to keep up with the same color coding, then I'll do this. Okay, and I know for sure water is going to be a liquid. Okay, so as a reminder, the subscripts do not come along for the ride. The whole point of the subscripts is just to balance the compound. So now that we have the compounds balanced, I'm just going to double check the state of this, or the solubility of barium acetate. So let's go to our data booklet. All right. So we have our acetate ion here. Most things are soluble, but let's just double check to make sure barium isn't part of it. Our exceptions. So barium acetate isn't part of our exceptions, therefore it's going to be soluble in water. Okay, so now that we got the states all done, let's just make sure this is completely balanced. So we have 1 acetate ion coming in, 2 acetate ions coming out, so I need to write a 2 coefficient in front of this. So that 2 didn't just affect the acetate ion, it also affected the hydrogens. Okay, so I gotta make sure that we have the right amount of hydrogens going in. So we got 2 hydrogens coming in, so that means I need 2 hydrogens coming out. Okay, how I'm looking at water is it's made up of 1 hydrogen and a hydroxide, just to make my life easier. Alright, barium, we have 1 coming in, 1 coming out, and with hydroxide we've got 2 coming in and then 2 coming out, so we are golden on there. Alright, let's organize our information. So what we just did right now, that was step 1, create a balanced chemical equation. So now I'm going to organize the information that the question's given me. So what exactly has the question given me? Well, it's told me that we're working with 25 milliliters of acetic acid. So let's organize that. So volume is 25 milliliters, but we're going to want to convert milliliters into liters. So as a reminder here, for our metric conversion line, There we go. Alright, so there's our metric conversion line. So we're starting off with milli, and we want to go to liters, which is a base unit because it doesn't have a prefix to it. So starting off at milli, 1, 2, 3 to the left. That's how many spots I move the decimal. So 1, 2, 3 to the left. So volume is equal to 0.025 liters for acetic acid. Okay. Now, they've also told us that the concentration of our barium hydroxide solution is 0.04. So let's write that out. And for our volume, that's going to be found on the titration curve. Okay, so that's why we want to figure out what the equivalence point volume is, because that tells you how much of your titrant that you used. So we said that we used 33 milliliters to get to our equivalence point volume. So let's write that out. 33 milliliters, and we know that we need to move the decimal over 3 spots to the left. So that's going to be 0.033 liters. Okay. So I'm going to have to erase this just so I have enough space. Now that we have our information organized, we can move on to step 2 of our Stoich steps, which is find the moles of your given substance. So the substance we've been given the most information for is barium hydroxide, so let's start there. Okay, so we got concentration is equal to moles divided by volume, and since we want to find the moles of our given substance, we need to isolate for N. So I got to ask myself, okay, what is volume doing to moles? Well, it's dividing, so we got to do the opposite, which is multiplying. So these cancel out, and my formula is going to be volume multiplied by concentration is equal to moles. So this is going to be the formula that I use, and I'm just flipping it around. So the volume and concentration have to belong to the same substance. So that's why I like organizing my information. I'm going to use the concentration of barium hydroxide and multiply it by the volume of barium hydroxide. Okay, and I need to use liters for the volume so that the units cancel out. 0.033 liters times by okay, so liters is on the top and the bottom. They cancel out. Alright, so if I take 0.033 times it by 0.04, we're going to get 0.00132. And that's going to be moles of barium hydroxide. Okay, so step 2, find moles of your given, done. Step 3, use your mole ratio to convert moles of your known substance to moles of your unknown substance. Okay, so I'm going to go times by fraction sign. So our known substance, that was barium hydroxide. Our wanted substance, so because it says calculate the concentration of acetic acid, that's what we want. So I should have put concentration, we don't know there. Alright, now the coefficients in front of both of these, so there's a 2 coefficient in front of acetic acid and a 1 coefficient in front of barium hydroxide. Remember that if there's not a number in front of your substance, then there's an invisible 1. Alright, so essentially we're just multiplying this by 2. So 0.00264. So that's moles. And now we're at step 4. Give the question, what it wants. So the question is asking for the concentration of acetic acid. So going back to this formula, concentration is equal to moles divided by volume. What this tells us is we need to take the moles of acetic acid and we need to divide it by the volume of acetic acid. So the volume of acetic acid is at 0.025 liters. Okay, so maybe I'll write this equation just a little bit lower here. So 0.00264 moles divided by 0.025 liters, and we get 0.1056. Moles per liter. And let's look at our question here. Looks like they gave us this in 3 sig digs, but this number has 2 sig digs. Reminder that leading zeros do not count as significant, but trailing zeros do. And of course, non-zero digits count as significant. So 2 sig digs is what our answer needs to be in. So I'm going to count 1, 2, there's my cutoff line. So it's 0.11 moles per liter of acetic acid. Alright, so there's a little error in the notes here. This example is just supposed to be written on the next page, but that's okay. So it tells us we've got 10 milliliters of sodium hydrogen carbonate is titrated with a 0.01 mole per liter solution of hydrochloric acid. So again, quick reminder here, titrated with. That's important wording so that you know whatever substance comes afterwards is going to be your titrant. So maybe I'll actually write that closer there. This is our titrant. Okay, so that must mean the sodium hydrogen carbonate. That's going to be our sample. Okay, so hydrochloric acid, we know that that is one of our strong acids. How you can know that for sure is if you go to your data booklet and you go to page 8 and 9, you'll be able to find hydrochloric acid right here. So since it's above this gray hydronium line, that's how you know it's a strong acid. Anything below this gray hydronium line is going to be a weak acid, okay? And of course water is neutral, so it doesn't count as a weak acid. Okay. So with this, I'm just going to label the same parts that we did on our last pH curve or titration graph, whatever you want to call it. So we're going to be labeling the endpoint as well as the equivalence point on the graph. So like I said, what you want to do is just draw some lines to help your eyes focus on what is the steepest part of this curve. So if I look, I'm going to say between there is about the steepest part. So I'm going to eyeball the middle of that, which looks to be right about there. And just draw a line here. Okay. So with this, we are kind of estimating where this is. So just so you know, each one of these tick marks is worth about 0.4. Okay. So I'm going to say this is going to be a pH of about 8.5-ish. Okay, so again, there is a bit of wiggle room with these answers here. If you said 8.3, 8.6, somewhere around there, then that would still be acceptable. With the equivalence point volume, let's draw another line just going down. So this one's a bit easier. That's going to be at 38 milliliters. Now we're going to label the buffering area. As a reminder, the last plateau is never the buffering area. So I'm going to focus on the first plateau here, and that will be my buffering area. Because this is just the area that is resisting changes to pH before it kind of gives up, and then there's a massive change in pH down here. Okay. All right, next part, determine what indicator would be appropriate to determine the endpoint for this titration. All right, so with this, there's a couple of different indicators that we could use. So let's go to our indicator list. All right, so since our endpoint was 8.5, so we could use phenolphthalein, or we could use, let's see what else we can use. We could use Cresol Red, and it's just with the last one here, the yellow to red part, that we could use. Another indicator that we could also use would be thymol blue, and that would be 8 to 9.6, the yellow to blue change that we could use. So as I said, there's a few different indicators that we could use. What I'm going to do is I'm just going to be focusing on, actually, you know what? I'll write all of them. All right, so I'm just going to start off with thymol blue. And for this, the color change, again, we're doing it from the start of the pH curve to the end point. Okay, because that's the color change that we care about the most. All right, so looking at the beginning here, we've got a pH of, we'll say 12.4. Okay, so at a pH of 12.4, okay, thymol blue is going to be 9.6 and above, so it's going to be blue. As a quick reminder here, for indicators, the right-hand number corresponds to the right-hand color. The left-hand number corresponds to the left-hand color. Okay? The in-between range corresponds to the in-between color. Okay, so since we're starting at 12.4, that's why I'm saying, okay, it's above 9.6, so it's going to be blue. Okay, and at the end point, let's say start and then end point. So the end point was 8.5, which is the in-between part, or it's a number in between the range. So we're going to be in between yellow and blue, which is green. All right, let's do Crescel red next. And I'm just going to follow the same format. Okay, so again, starting at a pH of 12.4, let's take a look at what that color is going to be. So with Crescel red, this is where we're looking. Okay, so 12.4, that's above 8.8, so that's going to be red. And the endpoint, which is at 8.5. Okay, that's going to be an in-between number, so it's going to be the in-between color between yellow and red, which is orange. Okay, next we could choose phenolphthalein. So for our color change, again, we're doing the starting color and the endpoint color. So with phenolphthalein, so we're starting at 12.4. So that's going to be pink because it's above 10. Okay, and then at a pH of 8.5, we're in between 8.2 and 10, so we're in between colorless and pink, so that's just going to be a very light pink. Okay, so on an exam, if you were asked this question, I would expect you to pick one indicator and tell me the color change for that specific indicator. The reason why I did 3 was just to show you some examples of what other indicators could be, and also just to show you that sometimes there's more than one possible answer. Okay. Last but not least, we are asked to calculate the concentration of sodium hydrogen carbonate. All right, so this is when we get back to our steps of stoichiometry. So step 1, create a balanced chemical reaction. Okay, so looking at this sentence up here, we're told that sodium hydrogen carbonate is titrated with hydrochloric acid. So sodium hydrogen carbonate. Now what I'm going to do, the same as last time, I'm going to color code the cation here. Right, so one thing I want you guys to be aware of is if we go to our periodic table and look at list of polyatomic ions, you're going to see hydrogen carbonate here. So let's see, right there. Okay, so hydrogen carbonate, you treat that as the polyatomic ion it is, and it's being paired with sodium. Okay, so our cation here is going to be sodium. Our anion is hydrogen carbonate. Sodium likes to have a +1 charge. Hydrogen carbonate likes to have a -1 charge, so they're balanced. All right, now we said that this is reacting with hydrochloric acid, so let's write that out. Remember, acids are always aqueous. All right, so we have a compound reacting with a compound. That means it's going to be a double replacement reaction. So sodium's going to take the place of hydrogen. Hydrogen's going to take the place of sodium. Okay, so for my first product here, I'm going to focus on what the product with hydrogen carbonate would be. Now, since hydrogen, this one right here, takes the place of this sodium, we're going to end up with 2 hydrogens. So I'm going to put this as, and let me color code this, H2 CO3. So one of these H's is this hydrogen right there. Okay, and then for our last product here, this is sodium going to live with chloride, so that's sodium chloride. And I know that is soluble in water because that's just table salt. Okay, but if you wanted to, you could look it up in your solubility table. Let's see. So chloride ions with most anything is going to be soluble. Sodium is not there in the list of exceptions, therefore it is soluble. Okay. Now with H2CO3, if we're looking up that one, so carbonate, that's right there. So it is soluble with group 1 ions and ammonium, which hydrogen is a group 1 ion. What it means by that is, can you find it in the first column of the periodic table? So this one right here. And absolutely, yes, we can find hydrogen in group 1. So that means this is going to be soluble. Another thing that you can do to figure out the solubility for H2CO3 is you could recognize that this is an acid, and acids are always aqueous. Okay. Oh, and I better color code this. Okay. Now, we got our skeleton equation here. Let's make sure everything's balanced. So we got 1 sodium going in, 1 coming out. We've got 2 hydrogens going in, 2 coming out. So that's balanced. We got a carbonate going in, a carbonate coming out. That's balanced. I already did the hydrogens, so now we're on to the chlorides. 1 going in, 1 coming out. This is balanced. All right. So balanced chemical equation, done. Let's organize our information here. Okay, so we're told that we use 10 milliliters of sodium hydrogen carbonate. So let's write that. Okay, but we know we should be writing this in liters, so we got to move the decimal over 3 to the left. 1, 2, 3. So that's going to be 0.01 liters. Okay, the question says calculate the concentration of sodium hydrogen carbonate. So I'm going to go concentration, no clue. All right, let's go back to the question. So we're told that we use a 0.01 mole per liter solution of hydrochloric acid. So let's write that out. And the volume of it is going to be our equivalence point volume, which we said was 38 milliliters. Which, if we convert to liters, that's going to be 0.038 liters. Okay, so step 1, balanced chemical equation. I also organized my information. Now step 2, find the moles of your given. So the given substance is hydrochloric acid, so let's start there. So going back to the previous question here, I'm going to start off with this formula. Moles is equal to volume times concentration. Okay, so remember my concentration and my volume needs to come from the same substance. So 0.038 liters for hydrochloric acid multiplied by the concentration of hydrochloric acid. So 0.038 times by 0.01, that's just going to give us 0.00038. Now, what my calculator has done is that it's given me the answer in scientific notation, so 3.8 times 10 to the power of -4, but we could also write it without scientific notation as well. Okay, so how this is the same number is that if we look at 3.8 times 10 to the negative 4, which is what I got in my calculator here. So the negative 4 is just telling me that I need to move my decimal 4 spots to the left, because a negative exponent just means that your number is in between 1 and 0. Okay, so moving my decimal 4 spots to the left, 1, 2, 3, 4, right? That's why 3.8 times 10 to the negative 4 is the same number as 0.00038. Okay? This one's just in scientific notation. This one is just written normally. Both are the same number, and you could write it either way. Alright, so this is the moles of our hydrochloric acid. Step 2, find moles of your given. That is done. Now we need step 3, mole ratio. So times by fraction sign. So we want sodium hydrogen carbonate. We are given hydrochloric acid. Okay, so this is a 1-to-1 ratio, so it's not going to change the number. But now this is moles of sodium hydrogen carbonate. Okay, the reason being, if you treat hydrochloric acid kind of like a unit, we've got the same unit in the top and the bottom, so they cancel out, and we're left with sodium hydrogen carbonate. Alright, now we're at the point in the previous question where I used this formula here. Okay, so we are at step 4 now. Answer the question, and since the question asked us to calculate the concentration of sodium hydrogen carbonate, that's why I'm using that formula. So concentration is equal to moles divided by volume, 0.00038 moles divided by, now the moles of sodium hydrogen carbonate have to be divided by the volume of sodium hydrogen carbonate, which is 0.01. Okay, so if we go divide by 0.01, that's going to give us 0.038 moles per liter of sodium hydrogen carbonate. Okay, now looking at the question here, we need to take care of sig digs. So this has 3 sig digs, and this has 2 sig digs. So I need to rate my answer in 2 sig digs, which, if I look at it, is already in 2 sig digs. So I'm done.